All right, so in this video, I'm focusing on how you can find and classify different maxima or minima, and also how you can find points of inflection. And we're going to do this all just using the functions and their derivatives, mostly algebraically. But I want you to keep in mind the picture of what we're trying to do. If I have a function that looks something like this, let's make that a little flatter and then go up like this. There are three different types of critical points. These three are critical points right here. In other words, these are the three types of things where our derivative could equal zero. So just because you find a place where the derivative equals zero does not mean it's a maximum, a minimum, or a stationary point. It's still, you'd have to work harder to figure out what type it is. And the first derivative test lets you just use the first derivative to classify. So the first derivative test basically says, look at this. So you find, let's just say an n such that f prime of n equals 0. Then if f prime of x is less than 0 for x is less than n, and that's not an and excuse me, and f prime of x is bigger than 0 for x greater than n, then n is a minimum. So what did I really just say here? I said that if the derivative, if the slope is negative when you're on the left side of the function, and if the derivative is positive when you're on the right side of the critical point, not the function, for the right side of the critical point, then n is a minimum. And I could say f of n is a minimum, or I could even actually say n comma f of n is a minimum. So I'm talking about right here. You see how the derivative is negative before it and the derivative is positive after it? That's why that's a minimum. You can flip that definition around and say that if f prime of x is greater than 0 for x less than n, and f prime of x is less than 0 for x greater than n, then n comma f of n is a maximum. If, however, because that looks like this part here, the derivative is positive, the derivative is negative, maximum. Derivative negative before it, derivative positive after it, minimum. And then the other option is that it's like positive and then positive, so that's a neither. Same idea, we could draw it over here where it flattens out, but it's negative and then negative. Or, sorry, that's positive and then positive. We could draw a stationary point going down like this, where it's negative before it and negative after it. Okay, so that's the first derivative test. The second derivative test instead looks at the concavity. So if your first derivative is 0, but your second derivative is negative, you have a maximum. If your first derivative is 0 and your second derivative is positive, you have a minimum. If both are negative, if both are 0, then you have a stationary point. Right there. Okay, so let's look at some examples. Let's look at y equals x to the 6th minus 6x. If I take the derivative, I get 6x to the 5th minus 6, which have a 6 in common. 6 times x to the 5th minus 1. And remember that my goal is to figure out where this equals 0. So if I set this equal to 0, I can factor that to be x minus 1 times x to the 4th plus x to the 3rd plus x squared plus x plus 1. This tells me that I really only have a single point of x equals 1, because this part over here is not going to equal 0, unless you consider complex numbers. If you think about what x to the fifth minus 1 looks like, x to the fifth minus 1 is a function that just basically looks like this. And so it's only going to hit the intercept at one point. So I really only have one critical point. So I have two options. I can do the first derivative test, which means I look at numbers to the left of 1 and to the right of 1 and talk about what the derivative is. So let's do that. So let's look at what is f prime of a number smaller than 1. F prime of 0 would be 6 times 0 to the fifth minus 6, which is a negative number. Now let's look at a bigger number that's bigger than 1, like f prime of 2. 6 times 2 to the fifth minus 6. I don't need to calculate it all the way because I know that that's going to be bigger than 0. And so I have a function that is decreasing, flat, and then increasing. So I know that this has to be a minimum. The last thing that I usually like to do is actually get the value when x equals 1. And so if I plug in x equals 1, I get 1 to the sixth minus 6, which means negative 5. And that tells me that the point 1 comma negative 5 is the lowest point that my original function looks at. Maybe you don't like the first derivative test, and so you can always do the second derivative test. 6 times 5 gives me 30, so I have 30x to the fourth, which is always greater than 0, or equal to 0, I should say, always greater than or equal to 0, because anything to an even power is going to be non-negative. And so that means that I always have a smiley face shape, a concave up. And so I can identify again that this has to be a minimum. Let's look at one other example that maybe is a little bit more interesting. Let's see, what if we had y equals 3x minus 5 minus 1 over x. So then y prime is going to be 3 minus, let's see, I'm thinking of this as being x to the negative 1. So that would be, I drop the negative 1 in front, so it's plus to the negative 2. So in other words, it's 3 plus 1 over x squared. If I want to make that equal to 0, then I can multiply everything by x squared, and I get 3x squared plus 1 equals 0. And that leaves me with 3x squared equals negative 1, x squared equals negative 1/3, which has no solutions. So what does that tell me? That tells me that this function has actually no critical points. So this function does not have a local maximum or a local minimum. I know that there is an asymptote because of the 1 over x part, but I know that there are no other points on it. Let's make a slight adjustment to it, and we'll see how it changes things. Let's pretend it was 3x minus 5 plus 1 over x. Then my derivative becomes 3 minus x to the negative 2. And if I make this equal to 0, I have 3 minus 1 over x squared equals 0, multiplying by x squared, adding 1, and dividing by 3, telling me that I have 2 critical points at positive or negative square root of 1/3. So I could do the first derivative test or the second derivative test. Let's do the, it doesn't really matter. Let's do the first derivative test. So sometimes it's nice to make a number line where you mark your critical points on it and choose values in between. So for example, a value here would be negative 10. a value here would be 0, and a value here would be positive 10. If I plug in y prime of negative 10, I would get 3 minus 1 over 100. That's positive. If I plug in a number like 0, chose a bad number. You can't plug in 0. So I need a number that is, this is a good example, because when you have a discontinuity at 0, you need to look at values on either side of it. So let's break up our number line a little bit more. Forgot about that detail. Let's look at negative 0.01, and let's look at positive 0.01. If I plug in negative 0.01 and I square that, I get a very large number. And so I have a very small number. 0.01 squared becomes 0.0001. And if I divide that by 1 divided by that, I get 10,000. So 3 minus that is going to be negative. So this value right here, y prime is less than 0. Same exact thing here, y prime is going to be less than 0. If I plug in positive 10, just like I did with negative 10, I'm going to get greater than 0. So what I found is that my function is increasing, flat, decreasing, discontinuity, decreasing, flat, increasing. So what we found is that this value here is a maximum, this value right here is a minimum, and then this value right here is a vertical asymptote. So you can see how using this, you can start to get pretty good sketches of what the graph of the function should look like. The last thing I wanted to do was just take the second derivative and see that that would give me 2x to the negative 3. In other words, 2 over x to the third. And you can see that this second derivative, this second derivative, y double prime, is going to be negative here. When I plug in a negative number, it's going to be negative. Well, that's what a maximum looks like. And when I plug in a positive number, it's going to be positive, and that gives you a minimum. So please comment, ask questions if anything doesn't make sense from what I did, and I will help out.